Hello, this is the course of data structure and algorithms. This is the chapter about BFS. We are going to learn about the breadth first search. So last time we already learned about the DFS. D means depth, but now we are going to learn about breadth. Okay, what is the difference between depth and breadth? So let's see. And I took this slide from the book Goodrich, Tamasya Code Data Structures and Algorithm in Python. Yeah, this is about the BFS. Oh, sorry. I guess I didn't update this one. Yeah, it should be about BFS. Yeah, okay. What is breadth first search? Before we go into the details of breadth first search, I would like to explain more things how the graph is important, especially in our field, like in the domain of industrial engineering. The first is path graph. If you still remember path and cycle in the graph, now we can draw the path graph. If you still remember in the DFS, we also learn about the concept of we learn about the spanning tree, okay, and we learn about tree, we learn about forest. In the graph, we can also draw path. Okay, so path usually it can be also called as linear graph, and in this graph, it is a path. Okay, so there is a kind of definition. It is a path with at least two vertices is connected and has two terminal vertices. Vertices that have degree 1 while the others have degree 2. So if this is a graph, okay, I want to have a path. So you already know the path from the graph concept. Okay? So this is one path, okay? And we call it, this is the path graph. If you know, you still remember the path, simple path. So this is the simple path in the graph, and we can draw the path graph. Okay? Paths are often important in the roles as subgraph of other graphs. So this is a subgraph, okay, and in which they are called as paths in that graph. Yeah, you learn about the path and you learn about the cycle. We can have the path graph and we can have the cycle graph, and both of them are part of the graph. The other kind of graph we can learn is the bipartite graph. What is bipartite graph? Yeah, it is a graph, or we call it bigraph. It is a graph whose vertices can be divided into two disjoint and independent sets. So two disjoint and independent sets U comma V. So we have U, okay, and then we have V. And those two are the collection of vertex. So we have vertex 1, vertex 2, vertex 3, vertex 4, vertex 5 in the U. And we have another vertex, which is vertex 6, for example, 7, 8, and 9. And for this one, we want to connect for each vertex in U with a vertex in V. So there's an edge. So this is the edge. So this is the edge. So we call this is a bipartite graph. Every vertex in U is connected with one V, one vertex in V. Okay. So bipartite graph are used extensively in online space. So usually, it's related with the e-commerce or advertising. For example, this one is one example: user and items. So these users and items, actually, we have the information. You go to mart, you go to online store, and then you buy something. Okay, let's say you buy rice. Then you can know that, okay, you gave the rating. The vendor who sell the rice is very good. Yeah, you give the rating 5. And then the other items is not that good, 1, because yeah, the vendor is bad. And for example, 0, because maybe this user didn't buy anything. And this one also 0. So this user, this is a user, this user didn't buy this product, this user didn't buy this product, so there is no rating, and so on. So using this kind of metrics, you can like recommend some products to this user if there are another good products. So this graph is called as a bipartite graph, and it is not a usual graph because you have the U, and then you have V, and then you have E. So U and V, they are the set of nodes. Okay, you can see here is the set of nodes, and then E is the set of edges on the graph. So this is the set of edges in the graph. There's another concept, the graph, where you want to use the existing data structure. For example, graph structure stack. Okay, what is graph structure stack? If you are doing with the graph, yeah, it's very flexible on the application. When you use the graph with tree, you use the graph with stack, you use graph with queue, you want to use graph with the recursive, you want to use graph with linked list, yeah, everything is possible. Now, yeah, I just want to explain just very briefly about some concepts on graph. So we call this is the graph structure stack. So we combine the stack and we combine with the graph. And usually we have this kind of stack, okay, stack with graph structure to figure out the grammar, you know, context-free grammar. Whenever you write something, okay, when you write an English text, for example, you will distinguish the word according to the context. For example, yeah, what is the adjective? Is there a noun? Okay, and the noun, for example, yeah, we know that it is an adjective and this is a singular noun. And then, yeah, we want to check whether it is a kind of sentence or not. So, for example, the little boy ran quickly. Okay, so the means the adjective. Little means the adjective. Boy means noun, singular. So the little boy, it contains one noun. Okay. And then ran, it is a singular verb, and quickly it's an adverb, and both of them, they contain verb. Because we have noun and we have verb, so we can say it is a sentence. So using this kind of graph structure, it is very important if you have the grammatical checking tools. So using this kind of idea of graph, it will be helpful also for making your algorithm. For example, yeah, this is another way to think about the stack. Okay? So there are 4 stacks like 7, 3, 1, 0. So it is a kind of root. Okay? So the 7, it can go 7, 3, 0. And it can be 7, 4, 1, 0, 7, 1, 0. And then we have 7, 5, 2, 0. And we have 8, 6, 2, 0. Okay. So this kind of stack is about the for example, if you want to do some kind of machinery, okay, in the production or in the manufacturing domain. So the raw material will work from this one and go to this one, go to this line, go to this line, and then this is the finished product. So this line is another part or another product, and you will go to this line, you will go to this line, and then here is the assembly. Yeah, that kind of idea that it can be also figured out by the graph structure stack. Okay. What we already did before, it was about the graph traversing. If you still remember the traversing, okay, the in-order traversal, the pre-order traversal, post-order traversals, those are the concept in the tree. And at the time, we define the tree, and we want to know which node that we visit at the first time. The same with the graph. We have the concept of graph traversing. Okay, so the graph traversing means how can we visit the node, and we can use stack. Last week we already, in the previous video, we already learned about the concept of DFS, depth first search. So this concept DFS is a graph traversing with stack. So the idea is the same with the graph traversing with the stack. We want to visit all the nodes, okay, but we need to set the starting point. Let's say the starting point is S. Okay. So we want to visit the first neighbor of S. The first neighbor, let's say I want to visit T. Then, visit neighbors of that neighbors. So for example, I want to, because I have already S and then T, okay? So T is here. And then I want to go to the next neighbor. And the next neighbor, here, I choose V because it is depth. Depth, it means I just want to go to the next child, the next child, the next child. If you go to the U, it means you go to the, not the next neighbor, but it's the neighbor of S. Okay? So that's why we choose V. Okay? And then after V, we want to choose another neighbor, which is U. Okay, we can choose this one. Okay, and then we choose another neighbor, which is W, and then we choose another neighbor, which is X. So this kind of stack, I think you already learned in the TFS, whether it is discover or package. Okay, so we can also do something with this idea for the graph traversing, or we can also do with the queue. Okay, if we are doing with the queue, then it means we want to learn the graph traversing. Oh, it's not the depth first search. Oh, sorry, I make of mistakes on this part, I guess. So actually, this not this one is about the BFS. Oh, yeah, I think last time we learned about the DFS, yeah. But with the Q, it is related with the BFS, but it's not totally about BFS. So let's see about the idea. So we want to visit the node starting from S to all the nodes. So you can see if it is about the Q, okay, visit the neighbors of S. Okay, so this neighbor of S, this is T. So we will choose T and then go to the Q. And then visit neighbors of neighbor in turn. Okay. So we have the neighbors of the neighbor here. We want to visit the U. And then we put U. So T will remove. And then we will visit U. Okay. And then we visit V. And then we visit W. And we visit X. So every nodes have the neighbors, and we want to select based on the first in first out concept. So those kind of things, it can be used with the graph traversing approaches. Now we are going to learn about the breadth first search. Okay, the idea of the graph with stack, graph with queue, it can be applied. You can use the stack to traverse all the graph. You can just use queue with the concept of graph, but there is another concept of what search, which called as the breadth first search. Breadth first search is a general technique for traversing a graph. So this is also another graph traversing. The BFS traversal of a graph, it is visit all the vertices and edges of G and determines whether G is connected, and it computes the connected components of G. And it computes a spanning forest. Okay, what is spanning forest? So you will see there are a lot of tree Yeah. So the unconnected component graph, they will contain of several trees. So a forest is a collection of trees. So you need to make the spanning forest using the breadth first search. In the concept, BFS will run n plus m. N refers to the vertices and m refers to the edges. So the BFS can be further extended to solve other graph problems. For example, if you want to find and report a path with minimum number of edges between given two vertices. So like, yeah, you want to go, this BFS is good for the navigation. And you want to find a simple cycle. Okay, the BFS is also good for that one. So this is the algorithm. And yeah, we are going to check the details of this algorithm with the example. The same with the DFS, it starts with the BFS algorithm and then given the G is the graph. And then the input is the graph and the output is to label the edges and the partition of the vertices of G. For all U in G vertices, so it is a collection of the vertices, set the label U unexplored. And then for all edges E, set E unexplored. And after that, let's make the vertices. If the label is unexplored, then let's go to the BFS G, S. So V will be the first vertex. So you can see here the BFS G, S, you will make L0. L0 is the new empty sequence. And then L0 will be added with a value which is the last one, is S. And then we want to set the label S as visited and then do this while loop. Okay. If the I now is 0, is not empty, then let's do I plus 1. So it means L will be 1 and the L1 will be a new empty sequence. You can do it this one. Okay, you can check the element, and if the element the E, if we know all the incident edges of the V, then check. If the label is unexplored, then check the opposite. Okay, so if we know the opposite, let's check whether the label, the W or the node in the opposite is unexplored or not. If it is unexplored, then yeah, you can set the label, you can set the edge as discovered and you can set the node as visited. So we have the Li plus 1. Okay, if it is I plus 1, it will be added with the node W, which is the new node that we already visit. If it is not, okay, then we will just use cross. So it's not back edge, but it is cross. Okay, so let's see one by one. How can we do this one with the example? So this is the code in Python. I guess we will learn how to deal with this one in the next video. Yeah, we have the blue color, which is the unexplored vertex, and then the yellow color, which is the visited vertex. Okay. Now, let's see. I will have the A, okay, and then I will have the B. I will have C, D, and then I will have E. I will have F, okay, and then I will have L, and then I will have I. Okay. In this example, the line, this line without any arrow, it means unexplored edge. If a line with the arrow, it refers to discovery edge. If a line with the dash line, it means cross edge. Okay, so it's different. So I can say, for example, this is D, okay, just small d, and then this is small c, and then let's say this is small u. Okay. Now, assume that I want to start from A. Okay. So A is the starting point, or maybe we can start here. For all u, the vertices, we just set unexplored. Okay, then I can put this one unexplored. U, and then U, and then U, U, and U. Okay, and then I want to set all the edges as unexplored. Okay, so it means unexplored U. Okay, and then this is also U. Okay, so everything is unexplored. After you put the unexplored, now you will go back to the vertices and check if the label of V is unexplored. Let's do the BFS G, V. Now let's see. I'm starting the search from A. Okay, I'm starting the search from A. We have the graph, comma A. Okay, so this is the starting point. This is A, and then L0 is the new empty sequence. L0 at last S. Okay, then what I can do is when L is 0, okay, let's say this is the index, okay, and L is 0, I want to add the A. Because I want to add the last, which is S, okay? And then set the label S as visited. So I change this one into, maybe it's better to, okay, just now it's not U, is not unexplored, but it becomes visited. Okay, become V. And then after I check to V for this one, I have I, which is 0. So I now equals to 0. You will check the L. What is L? L now, because Li, I is 0, Li is empty, not. Okay, so this is the not symbol. Yeah, it's not empty. Then you will do the Li plus 1. It is a new empty sequence. Then you will have Li plus 1. 0 plus 1, it means 1. And you want to put this as an empty sequence. Okay, no problem. I just have the L1. And then I would like to check all the L1 elements. Okay. And I want to put a V, oh, Li. Okay, now I equals to 0. So what is the Li? Okay, I want to go to A. Okay, A is the element in L0. And as you know, you want to get all the edges. So we want to get what is the incident edge of the vertex V. So we have this one, this the first edges, this is the second edges, and this is the third edges. Now I want to check the label. If the label E is unexplored, then check the W, which is the opposite of B, E. Okay, this is unexplored. So I want to know what is the opposite. So the opposite is B. Okay, so the opposite is B. And yeah, the B, I would like to check. B is unexplored. Yes, right? Because B is unexplored, then set the label E as discovery, and then set the label W as visited. Then I need to change this one. It's not U anymore, right? But I changed to V. Okay, and after I know this V, or maybe it's better for me to draw in different color. Okay, so it is to avoid the confusion. I'll just green. Okay, so I visited this ads, and then let me change it now. Now the ads has been set as discovery, and then let's make the W as visited. Okay, so it means the W is the node. The node now it becomes visited, and after you visited that node, we want to add the W into the Li plus 1. So in this case, the I is 0. Okay. The I is 0, and yeah, L0 plus 1, it means L index 1. So the index 1 will have B. Okay. And after I have B, you can see here, yeah, because it is the condition is true, yeah, we will not do this else, so we will return back. So here, we go here, and then now I will like to check again. Is the E has finished all? Okay. If you check this one, oh, there is still another V here, A to C. Okay. So okay, this is the L0, and I put the L1. Yeah. Oh, I have another H to Z. If it is an H to C, okay, so here, if it is an H to C, another statement is to get the label E is unexplored. If it is unexplored, yeah, this is unexplored, then what we can do next is to get the opposite. The opposite of V comma E is C. Okay, this is the opposite. And what we can do next is the label. If the label is unexplored, okay, what is it? The label of the E is unexplored, then you put the, sorry, you have the label of W, which is the opposite, is unexplored. Go this one, E as discovery, and then W as visited. So here I can say, after I know that this is still not explored, so here is not explored, then I can have, let's say, so this one is explore, and then now it is explore, and then set the label W as visited. So C is visited. Okay, so C becomes visited. So the graph will be something like this one: L0, L1, and L0 contain only, yeah, the L0 contains only one, the L1 now contains two. Okay, so here is the C. And next, after we have this one, we want to check the, yeah, oh, we have the L1 at last W. And after we finish, we don't go to else because it is the if. And then we will go back again to the for loop. So we want to check whether there is another edges or not. Okay, we have another edge, this part. Okay, So we need to check again. The same. Let me erase the other one. So we will go to again next edges. So the next edges is the A to the next node, which is this one, A to D, and you will check. Get label E unexplored. Yes, this edge is unexplored, and then you will check again the opposite. The opposite of A with the particular edge E. So we want to get it as the W. So the W is D, and then I want to know D is unexplored. Yes, because D is unexplored, so the edge will be set as discovery, and then W will be set as visited, and then let's add the node into the Li plus 1. And yeah, I can set this one as discovery, and then D change to visited, and then D now has been placed here. Okay. After I finish this one, I will return back here. Is there any other edges from A? Oh, finish. Then there is no other edges, and I will go back to this for loop. What is this for loop? I want to check all the elements in the Li. What is Li? Because I is still 0. So what is the element? It's only A. Okay, then because we already finished with the A, we will do the next. Because we finished with the A, you will not do this one. After we finish with A, because we finish with this A here, okay, we finish with the A, then I will be I plus 1. Okay, what happened to this one? If I now 0, then it will be 1. Okay, when we go to the 1, it means it will go to the element B, C, and D. Okay. So after we have the I equals to 1, I plus 1, so we will return back to this while loop. Maybe it's to avoid the confusion. I will delete this one. Okay, I will delete this one. So after I equals to 1, it goes back to this while loop. And then now let's check. Li, which is L1, is empty or not? Yeah, there are 3 elements, right? So we have B, C, and D. So there are 3 elements. That's why we can say that, yeah, that's true. It's not empty. So we will have Li plus 1 as a new empty sequence. So we just make an I plus 1 now becomes 2. It is empty sequence. Okay, empty. And then what happen next is to get the all V in the Li elements. So all V, we have the B, and then we have C, and then we have D. And then let's explore the edges. So this one is starting from B. Okay. So first we just start from B, and then let's figure out all the incident edges of B. Okay, all the incident edges of B. So I guess later we need to check this one. First, we want to check the label, whether it is unexplored. Okay, because if you check this one, now the condition is here. Here is already explored. Then you will not do with this one. How about this edge? Okay, this is still unexplored. Let's see, because it is unexplored. Okay, and because it was unexplored, let's check the opposite. Okay, the opposite of the particular V, which is B, and then E. So I want to use this one. Okay, this one. And I want to check if the label W is unexplored. So C, we already visited C. Then it is already explored. It is already discovered. Then it will not go here, but it will go to the else. Else is the opposite. It is not true. It's false. So set label E as cross. Oops. So this one, it will set as cross. Now we have this one cross. Because it is cross, so we have the symbol, this one, dash line. Okay, not a solid line. And after we have this, we will do again the next, which is the after we have this, you can go to after we finish this one, we will check again to the edges. Now, is there any other edges from B? Okay. Is there any other? Oh yeah, we have this. Okay, we have this edge. Okay, it is unexplored. Okay, we want to get the label. It is unexplored. Yes, it is true. So we want to check the opposite. Okay, what is the opposite of B in the particular of E? And we want to check if the W is unexplored or not. Okay, we go to E. So E is unexplored. Oh yes, E is still unexplored. Then, because it is E is unexplored, we will set the E as discovery and then set label as visited, and then we will do the addition. So at last to the Li plus 1. So this will be set as discover. Maybe I can just erase this one, and then I can just change this into the green color. This one now becomes discover, and then I will choose the maybe this one. It will be better. Okay, so the line here, it shows the discover, and E. What about E? E now has been changed into the V. Oh, okay, just let me just use the green in order to avoid the confusion. Now E becomes visited, and I want to put the particular node into the list. So we have this one as E. Okay. Maybe yeah, I think to avoid the confusion, I need to yeah. So here is the E, and after I have the E, let's see, you can go to the next of the node, because I already have this ads. I have already have this ads. I already finished with this ad. So what we can do is going to the next node, which is C. Okay, we finish with all this step, and yeah, the edges in the incident edges of the B has been finished. Okay, no other edges. So we will check the other V. The other V now becomes C. So we want to go to C. Now let's see about the C. We want to check the incident edges of C. And let's put it on the variable E. And we want to get the E, which is unexplored. Okay. C, we have this already discovered. What about this? Is already discovered. What about this? Okay, it is not discovered. So we want to check. It is unexplored. Because it is unexplored, then I would like to get the opposite. the opposite of C in the particular graph is E. Okay. So I want to know this one. Yeah, this is E. What about E? E is already visited. Okay, whether E is whether E is unexplored. Yeah, because it's already visited, we will not do this one, but we will go to the else. So the else is going to this set label, and we want to set it as cross. Okay, so we have this one and this one as the cross. It means we cannot use this one as the discover edge. And after this one, we will go back to the E. And after you have this, you want to check what is the other edges. So C, yeah, we have another. This is not possible with this because it's already, if you go to this one, yeah, you will check the D. What is D? D is already visited. Okay. D is already visited. So it is not unexplored. Then it will go again to the cross. And then you will go to the next. You need to find the other edge, which is the incident edge of C, and you want to check which is an unexplored. Okay, so we can check this one. This is unexplored. What about this unexplored? Okay, we want to go to F, which is the opposite. What is the opposite of C? Yeah, okay, we have the opposite of C is F. Okay, and then F, we want to get the label. If it is unexplored, then yeah, F is still unexplored. So we want to set the label as discovery, and we want to set the W as visited and put I plus 1 with the new node, which is W. So we will give this one because it is not visited. Okay. So it is not visited. So we have this line as explore. Okay. So this one has been explored, and then we visited F. And after that, we will put F in the L2. So now F has been visited, and it is in the L2. Okay. And after I have this, finally, I will return back to this edge. Is there any other edges from C? Okay. Is there any other edges from C? No, because it's already visited. It's already cross, and already explored. So we will go to the next element of L1, which is D. Okay. Now we will check D. If you check the D, okay, you can see the E. Here E is already discovered, so it doesn't mean that you need to visit that one. This one cross, okay. And then what about this? This is remain unexplored, right? Okay, this remains unexplored, but F already visited. So yeah, you can just put this one as cross. The final result will be something like this one. Okay, so this is the final result of using BFS. What does it mean? It means you will go from A, you will check B and C and D. So it is the neighborhoods. After you check the B and C and D, you want to check from B, and then B you want to check whether it already visited A. Yeah, already. B to C already visited. Then you will just go to E, and then go to C. C already visited to A. C already visited by B. C already visited E. But how about C and F? Okay, because F is new, then it will go to F. So it means the breadth. Okay, breadth means you want to go to the neighborhood, and after you visit the neighborhood, you will go to the next neighborhood, and you visit all the nodes at the next neighborhood. Okay. So the properties that we use in the BFS, yeah, we use the connected components. connected component of S. So the property 1 means that I would like to visit all the vertices and edges of GS. As you know, yeah, we visited this one, we visited all the edges and we visited all the vertices. Okay, so we check all those things and then we put the label discover. We have the label, yeah, discover and cross. Okay, the discovery edges labeled by BFS GS form a spanning tree. Okay, so this is spanning tree. So this is the spanning tree. And after we have the spanning tree, then you can like just do with another algorithm to visit the nodes, for example. And the property tree, okay, the property 1 means I visit all the vertices and edges. The property 2 means I create the spanning tree, and the property 3 means that for each vertex in Li, there is a path. Okay, there is a path from S to V which has I edges. Okay, so the TS, it means the tree or the spanning tree from S. Okay, this is like, for example, this is the S. This is the starting point. It has the path from S to any of the node, okay, and it has the I edges. I means, yeah, something related with the, okay, this one is the Li. Okay, Li, you know that I, if we have 2 depth, then the I will be 2. So the path from the TS, it means from the starting point to V has 2 edges. 1, 2. Okay, 1, 2, 1. Okay, so you will know how many steps you will go to the last node. And every path from S to V in GS has at least I edges. Every path from S to V from any path, for any spanning tree, it will have 2 edges. Okay, so that's the meaning by Li. So the I here, yeah, is represent something. So if I equals to 2, then it means it will just have only 2 edges for visiting the other node. Okay. So the analysis here, it will take ON in order to just get or set a label. And when you try to label the vertex, because there are 2, okay, unexplored and visited. So just label twice, so the operation will take only twice. For the edges, also the same, it will be labeled twice. It is labeled as unexplored and discovery or cross. Okay, and for every vertex, it is inserted once into the sequence Li. So it means just one time into the list. The incident edges is called once for every vertex. So it's just one time. So the maximum will be just the number of vertex. So we can say that the BFS runs in ON plus M. Okay? N is the number of nodes and M is the number of edges, provided the graph is represented by the adjacency list. Okay, to still remember adjacency list. Yeah, we have the adjacency list, we have the edge list, and we have the matrix. So using the adjacency list, the computational time will be N plus M. Okay, please remember that you need to understand the big O, because whenever you do the algorithm, I will ask you to measure the big O. And for this BFS, you still remember the property of the graph. It will be like the degree of V equals to 2 multiplied by M. So the number of degree means the number of edges on a particular node, and then you will do the summation for all the nodes. Yeah. The application of the BFS, we can use the, this is to get the connected components. So what is the connected components of G? Yeah, it means you can go, let's say you have the navigation. So the navigation is using this kind of algorithm because it's very fast. It's not that long. Okay? And then you can compute the spanning forest of G. You can find a simple cycle of G and report that G is a forest. And given two vertices of G, find a path in G. And let's find the minimum number of edges or report that no such path exists. So usually this kind of things, yeah, is for the tracking, okay, or path building. You know that the DFS, okay, DFS is fine for the spanning forest and for connected component, for making paths and for making the cycles. Both BFS and DFS are good for this one. But okay, but for BFS, it is good for shortest path. Okay, so as I mentioned to you, many navigation use BFS instead of DFS. But DFS, actually, it is good for B connected components. So if it is like you have two connected components, yeah, you can calculate it easily. So there is a strength and there is a weakness between the BFS and DFS. So if you use the BFS, it is more relevant for the shortest path, but for the B connected components, it is relevant to use DFS more. When you have the DFS, you will have what we call as backends. Okay, the backends means the W is the ancestor of V in the tree of the discovery edges. You know the ancestor? Ancestor means the upper part or the parent. Okay. However, in the BFS, we call it the cross edge. The cross edge means the W is in the same level, okay, in the same level or as V, or it is in the next level. Okay. For example, if I know the C, okay, C will not check the A because it is the parent, but C will check the E because E already visited by B, then you cannot visit E again. So it will be the same level or in the next level. Yeah, I guess that's all for the BFS. And I hope that you understand the step-by-step of the DFS and BFS. Both of them are good algorithms in graph. And I guess it will be also good if you try, you can apply those two in your application or in your team project. Okay. And next video, I will try to explain with the code for DFS, BFS, and then I will let you know how can you do with your team project, especially when you share your files. Okay, it is very convenient to use the Google Colab. So in the next video, I will explain with the code, and you will see more things that you can do for your team project. Thank you very much for listening and see you on the next video.